Let's look now at the idea of exponential models. Now, when we think of an exponential model, we typically think of models that have the form f of t equals c naught e to the kt, where this value c naught we think of as an initial value. Now, specifically here, if we have a situation where k is greater than 0, for k positive, then we have a growth model. If we have a situation where k is negative, k less than 0, then we have what's known as a decay model. So if we look at a graph for k being positive, it will look like this. And see, if this is the t-axis, for t equals 0, e to the 0 is 1, I will have a value right here, initial value of what I'm referring to as c naught. Now, on the other hand, if k is negative, then I have a decay model, so a graph would look like this. Still, when t equals 0, I'll be at the y-axis at the value c naught, but the model decays. It gets smaller and smaller and smaller. And that should kind of make sense, because for k negative, this would actually look like c naught over e to the kt, where k is now positive. See, this is a negative exponent. When I have it written in this form, I can write it down here with a positive exponent. So as t gets bigger, this gets bigger, the whole ratio is going to go to 0, so it'll get very, very, very small. Now, consider an exponential growth model that has this form. F of t equals some initial value c naught times e to the kt. And what I want to do is take a look at a couple of the properties here that we see with exponential models. First of all, the rate of change is proportional to the current value. And that's kind of obvious as soon as we take a derivative. If I take a look at d dt of this value c naught e to the kt, well, that derivative is going to be k times c naught e to the kt. But you notice right here, this is my original f of t. So I could write this as k times f of t. So it's this value, f of t, the same thing we started off with, multiplied by some constant k. Hence the reason we say that the rate of change, this is the rate of change, it is the first derivative, is proportional to the current value. So at any value or any time t, f of t will give me the current value, but it's going to be proportional because this value k, we can think of this value k in this context as a constant of proportionality. So we can think of k as being the constant of proportionality in this scenario. So unlike a linear function, clearly the rate of change is not constant. It depends on the current value, and it's, again, proportional to whatever the current value is. Now, we often think in terms of relative growth rates. Now, if we're talking about relative growth rates, then it's obviously a growth rate relative to something. And the way we think of it here as the current growth rate divided by the actual current value. One way to think of that is how fast this thing or this function is growing now relative to its value right now. And I can represent this as f prime of t. There's my growth rate divided by f of t. F of t is going to be the current value. Well, that we said a moment ago, that f prime of t is k times f of t. This is the first derivative. These two are the exact same thing. So if I divide this by the current rate, which is f of t, obviously these f of t's will in fact cancel out, and what I'm left with is k. Therefore, I can say the relative growth rate is actually constant. So the growth rate is proportional to the current value, but the relative growth rate is actually a constant. Now note that this holds true for k being non-zero. So this would hold true for both a growth model and a decay model.